Hello and welcome to this video. We're going to do a combination of parent function review. I'm sure you guys have seen that before, and then we're going to jump into transformations and how those work. All right, so let's just go over the parent functions really briefly. So what we want to do is we want to complete a graph and include at least 5 points. You want to do this anytime you do any sort of function sketching. And then we're going to talk about basic properties like domain and range, increasing, decreasing, and then the end behavior. Those 3 things are pretty important, especially if you move on to calculus. So this is probably the simplest function you'll ever see. I like to call this the identity function, because the idea is you just plug in a number and the output is whatever that number was, right? So if you just plug in 2, you get 2. Plug in -1, you get -1, etc. Right? So we can pretty easily find 5 points, right? So let me put a few examples. Plug in 3, you get 3. Plug in, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10. And here's 10. And you get 10, right? Plug in 1, you get 1. -2, you get -2. So hopefully y'all can see, right? Just look like this. You want to put arrows at the ends to show that the graph goes on forever, right? So that's our graph. Domain and range are super easy, right? We're allowed to plug in every single real number. So you can put in all reals. Range, you can get out every single number. So all reals, all real numbers. You could also put interval notation, right? -infinity to infinity. That means the same thing. Increasing, decreasing. Determine where the graph is increasing and where it's decreasing. So keep in mind, we always consider this from left to right every single time, just like you're reading a book, right? So when you look at this graph, where is it increasing? Where is it decreasing? Well, increasing, it is increasing everywhere, right? So meaning, if I am hiking this graph, remember, we're always going left to right. This guy is going uphill, right? We never go right to left. Right, so that means we're increasing for the entirety of the graph, and we're decreasing nowhere. So you can say maybe none. You could use this fancy symbol. This is called the null set, right? It's just the set with no numbers, right? There's no place I'm decreasing. Determine where the function is headed, positive or negative infinity, 0, etc. So this is talking about the end behavior, right? So we can say the function moves, let's see, to the right. We could say right end behavior. Or we could just say right, just for short. This is going to positive, well, we don't have to write out the word. We can just write infinity. Right? As we move to the right, the function is going to positive infinity. As we move to the left, the function goes to negative infinity, right? So this is that negative infinity end behavior over here, and then this is that positive infinity end behavior there, right? All right, cool. Moving on. X squared. We call this, you can call it the squaring function. You can call this a quadratic. You can call this a parabola. These are all just different words for it. And what's nice about this function is all of its outputs are positive, no matter what you plug in, and you just square the number. So 2 squared would be 4. -1 squared. Remember to put those parentheses. You should get +1. Let's see, f of 3 would be 3 squared, which equals 9. f of, let's do -3, right? Also 9. So we just need to plot a few of these points, right? So 2, 4 would be around here. We did 3, 9, so let's see, here's 3, 4, 5, 6, 7, 8, 9. 3, 9. If we went to 4, we would get 16, right? When we plugged in -1, we got 1. And some of y'all might know this already, right? We have y-axis symmetry here. Plug in 0, we get 0, right? So basically, we can just reflect these points across the y-axis, and we get more points, right? And this guy over here. So we get this nice parabolic shape. You just want to have at least five points whenever you sketch anything. Cool. Domain. All reals. You can plug in any number you want. Range. This is only the numbers that are 0 or positive, right? So we have basically, like, if we were to shade in the range, we would have this point, and then we would have all of these. Remember, the range is sort of like the shadow that the function casts onto the y-axis. So our range would actually be 0 to infinity. Remember, we do not include infinity, that's parentheses, but we do want to include 0. 0 is a valid input. We can plug in 0, right? F of 0 equals 0. So just doing some quick math over there. I'm going fast because most of you guys know this stuff. I don't want to kill too much time. Increasing, decreasing. So in this case, a little different. Imagine your little hiker dude, right? He's going downhill initially, but then he's going uphill after 0, right? So what we do for increasing, decreasing is we do not include that point right there, right? Because that's going to be where he's not really going up or down. He's kind of flat, right? So what we say is he's going to be increasing when he is greater than 0. So that would be all numbers greater than 0 except for 0. Decreasing when he is at a negative x value, right? So this is like the left side when he's going downhill. This is the right side. Cool. Behavior and behavior, right? So if we talk about right and behavior, the function is going up and to the right, so it's goes to positive infinity. The left end behavior also goes to positive infinity, right? So on the graph, that's talking about this and that, right? They're both going to positive infinity. Okay, cool. Next up, we got the cubic, right? For this one, I would do some small numbers, right? So we can plug in 0. We get 0 cubed, which is 0. We can plug in 1. We get 1 cubed, which is 1. We can plug in -1. That gives you -1, right? So because this is an odd power, we get a negative answer there. Plug in 2. 2 cubed is 2 times 2 times 2, that's 8. And -2, be careful, -8. Sorry, I put an infinity symbol there, that's weird. So I have this point, 0, 0, 1, 1, -1, -1, 2, 8, so 1, 2, 3, 4, 5, 6, 7, 8. And then -2, -8, so -2, -3, -4, -5. Right there. So you notice this function gets steep very, very quickly. So if we were to connect these, we would get something kind of like this, almost like an S shape. All right, so cubics go to infinity very quickly. Call these a cubic. It's a cubic function. All right, so domain and range. Domain, what numbers are we allowed to plug in? All reals, right? Range, different from the quadratic, right? This one covers all real numbers as well, right? So you can get any output you want. So notice no matter what point we pick here, every point on this graph can be associated with any y value on the y-axis, right? If you were to think of the shadows here, we would basically shade in pretty much everything. In fact, actually, we would shade in everything, not just pretty much, right? So the range is all real numbers as well. All right, increasing, decreasing. Increasing, again, imagine your hiker guy always moving left to right. So here he is. He's going uphill here. And then here he is again. He's going uphill again. It looks like he's always going uphill, even when he's at the origin, right? The origin, he's also moving uphill. Which means we are increasing everywhere, right? So we would say increasing negative infinity to infinity, decreasing nowhere. That's the null set, or you could say none. And then lastly, end behavior. So right, if you look at the graph here, that's your right end behavior. That's positive infinity. So it goes to positive infinity. Left end behavior right there, it's going down. So the left end behavior goes to negative infinity. Cool. All right, square root. Now we already know something about the square root function. We are not allowed to put no negative numbers can go in there for the parent function, right? You cannot take the square root of a negative. So we should actually already tell ourselves the domain can only be 0 to infinity, right? Those are the only numbers we're allowed to plug in, and therefore the only numbers we can really graph on this function. So let's plug in a few easy ones, right? So 0, square root of 0, that equals 0, right? That is a defined value. F of 1, square root of 1, well, that's equal to 1. Let's do some perfect squares here. So skip over to 4, right? That'll be an easy one. Square root of 4 is 2. And let's skip on over to 9 as well. Square root of 9 equals 3. Now in this case, we can only really get 4 nice numbers here. If you try to find anything else, it's going to get a little messy, right? You run out of graph space. So we're just going to stick with these 4. So 0, 0, 1, 1, 4, 2, and then 5, 6, 7, 8, 9, 3. All right, so this is the graph of the parent function. So you might notice, right, if you look back up towards our parabola here, imagine taking that left side of that parabola, rotating it clockwise, you actually end up getting this exact shape, right? So that's not a coincidence. Square roots are kind of the opposite of squaring. So there's our graph. Our range, think about the numbers that this graph is covering on the y-axis, right? If we were to draw horizontal lines from each point on our graph to the y-axis, right? Basically, we would only shade in the top part of that axis, right? Nothing down here, right? There's no graph down there. So essentially, our range is the same, 0 to positive infinity. right? You can only plug in positive numbers and 0, and you can only get out positive numbers and 0. All right, increasing, decreasing. Imagine your little hiker dude. All right, so at different points on this function, he's going left to right. And no matter where you put him, he's always going uphill. Right, so we would say increasing, but again, only on your domain, right? You can only put these numbers. You can only put the hiker at those spots, right? So he's increasing everywhere inside of our domain. So that would be the entire domain, and therefore he's decreasing nowhere, right? There's no place on our graph where he's going downhill, right? Always uphill. Right end behavior, okay? Well, that would be talking about this arrow here. Now, you can actually go closer. Well, essentially, this end behavior is going to positive infinity. I know it doesn't look like it, but essentially, the bigger numbers you plug in, the bigger the output is, and you can make that output as big as you want. Essentially, without bound is what we would say. So the right end behavior is to positive infinity. The left end behavior doesn't really apply here. So we might say like NA, right, not applicable, because the function essentially disappears on the left side. It just sort of disappears. So there really isn't any left end behavior. When we talk about end behavior, we talk about these arrows that are telling you that the graph continues. Okay. Ooh, this is a very important one. Absolute value of x. So here we actually do already have the graph, which is super nice. You always get that super nice V shape, by the way. Anytime you do an absolute value function, no matter how it's been transformed. Right, so let me drop those points there. 0, 0, 1, 1, 2, 2, negative 1, 1, and then negative 2, 2. These are the 5 points that they're outlining here. Right. So essentially, absolute value, basically no matter what you plug in, just makes it positive. Right, so we would say absolute value of negative 2 equals 2. Right. Absolute value of positive 2 also equals 2. And so basically by the time you get to 0, 0 is kind of the border between the positive and the negative numbers. It just becomes itself, right? But everything else, if it's negative, it becomes positive, right? So that's how the function works. So we have the domain. The domain is you could plug in anything you want, right? But the range is only from 0 to infinity. And yes, you can plug in 0. That's perfectly valid. We are increasing at 0 and the positive numbers, right? So that would be hiker guy is over here. Right? He's going uphill. And decreasing from negative infinity to 0. Right? So hiker guy going downhill, right? Okay, so this is, I guess, the format of probably how they wanted us to write the answers beforehand. I just sort of created like a little summary. I would probably accept either way, right? So this is a little bit more calculus-y, right? So as x goes to positive infinity, f of x goes to positive infinity, right? So that's equivalent to saying like what we were saying here, right? So that's probably what we should have said. As x goes to positive infinity, f of x also goes to positive infinity. And for left-end behavior, you notice they do something different. As x goes to negative infinity, meaning we're sort of moving left on the graph, f of x goes to positive infinity, right? So that would be like, you know, we got x, f of x here. Right, basically, that's saying as you move to the left, your function is going down, right? As you move to the right, your function is going up. So, you know, this might be an example that I just made up on the spot. This has nothing to do with this graph, right? So, in fact, I should probably get rid of it because it's probably confusing some of y'all. So, anyway, If you want to know the most proper way to write your end behavior, this is it. But again, I'll probably be okay with stuff like this. That's fine. All right, so that's parent function basics. Those are the main ones, guys. There's really not that much out there. Maybe the only other ones we might learn later are the exponential, e to the x, ln of x. Those actually become really important for calculus, right? Super, super important. So we'll get to that later. That's like chapter 3, basically. So we're not going to jump in yet. So anyway, hopefully this was a good refresher on parent functions. Feel free to pause, go back if something didn't make sense. I was going fairly fast, right? Again, I'm assuming you guys know most of this stuff. And then in the next video, let's go over some transformations.